Hello, everyone. It is the last lecture of the semester for statistics. I have but one thing left to share with you. That is the second half of chapter 12, this little thing called regression. Now, regression might sound like a very big and scary topic or concept. That's because there are many forms of doing regression calculations. They get complex, they get complicated. But what we're going to do today here is actually relatively simple. Multiple regressions, a bigger deal. Curvilinear regressions, a bigger deal. But right now, we're going to do the simplest possible linear bivariate regression line. And I think you might even enjoy it. So what we did when we talked about correlation was we started talking about that line, the line that runs through the dots, not perfectly, but the best line to run through the dots. And we started talking about whether that line had a tendency to go through the bottom left and top right quadrants and slope up and give a positive correlation, or go through the top left and bottom right quadrants and slope down and give a negative correlation. But that line had always been kind of vaguely defined, an impression, but there's a way to get an exact description of one and only one line that is the best. What we're going to do for the purposes of this class is to talk about that line as the best guess we have about a y value given a specific x value. There's no particular reason why either one of the variables has to be x or has to be y. In this example here at the bottom right, we've got height and weight in a scatter plot. There's no particular reason height has to be the x variable, and there's no reason weight has to be the y variable. We could flip them and do all of this work again, get a different correlation. We have the same correlation coefficient, but we'd have different correlation numbers. We'd get a different regression line. That would be fine. It's kind of arbitrary. But once those variables are established, one is x and one is y, what we are after is a line that tells us, hey, if you've been given an x value on a silver platter, given the value, using that value to go a certain distance along the x-axis, when you go up the y-axis, how far should you go up in order to use our information to make the best guess as to what a person's weight would be? So in this case, we would know the height, but we would then guess the weight, okay? That is what a regression line is all about. That is what a regression line is for. So x is going to be given, but the y dimension is the one that's going to involve the uncertainty that we're dealing with when it comes to making a prediction or having the best line. The line that we're going to draw then is the one that fits all of those points the best, while minimizing the amount of vertical error between the guess and the actuality that are represented by the dots in the scatter plot. So this line turns out to be the line of most educated guess, the line of best guess. And it would look something like this. Okay, now is that exact? Is that precise? No, we haven't figured out how to exactly or precisely do it. But we know that it's going to look something like this because we can kind of intuit where it belongs. I'm not even going to do the procedure in the abstract. I'm going to go right into doing it with an example. And I'm going to talk about the relationship between studying, taking finals, and coffee. I spent the first semester of my time in college drinking no caffeine whatsoever as a weirdly committed, nobody asked me to do this statement or act of solidarity with my Mormon girlfriend, who wasn't a caffeine drinker either. And so there I did. But I know what it is like to go through finals week without drinking any coffee, and I never want to do it again. Okay, I broke my arm when I was in fourth grade. I never want to do that again, and I never want to go through finals without coffee. In fact, I don't ever want to go through a morning, but that's the backstory, all right? So the relationship between the average number of milligrams of caffeine consumed during finals week and the average number of finals that a person takes over their college career could be predicted to have a relationship. Now, I know that not every class you have gives a final. I know that not everybody takes the same number of classes. So the the pressure, the load on a person for is different. And so hopefully, if caffeine has anything to do with how many finals you take, there will also be a person-to-person difference in how much caffeine they consume. All right. So in other words, what we're going to do is designate the number of finals as the X variable, and then we're going to use the number of finals to predict how many milligrams of caffeine that person will have consumed. And then we're going to evaluate our best guess and say, typically, when we give our best guess, how far off is it from the truth? All right. It's as close as possible given what we know, but it's still going to be off by a certain amount. What is the typical amount that a guess is off given our example? Now, this looks really complicated, really scary, but what I've got here on the screen is everything that we would have needed to do to cover getting a correlation coefficient from the 10-person data set that I've made up about finals and caffeine. This is the entirety of the last lecture, all right? So what I've got here is person one drank an average of 1,378 milligrams of caffeine per day. They averaged 3.55 finals over their career. In order to get the correlation coefficient, I then would have had to know what the mean of caffeine is, that's 1,150, the mean number of finals, that's 3.14, and also the standard deviation for both. Standard deviation of 225 milligrams and a standard deviation of 0.57 finals. Using those bits of information, I can get z-scores for every single data point in this set. There were 10 people, each one gave 2 values, so there's 20 data points. That means 20 z-scores. These are the z-scores for everybody's caffeine intake. These are the z-scores for everybody's number of finals, and therefore, here in the last column, every single person is going to have a cross product. Their z-score for one variable times the z-score for another variable. You will notice that all but one of these cross products is positive. That means we are almost certainly going to get a positive correlation between the two. Oh, look at this. The sum of cross products is positive. That means that the correlation is definitely going to be positive. When you take the sum of cross products, you divide it by n minus 1, you get a correlation coefficient of 0.92. Very strong correlation. This is obviously fake and made up data, so there might be a reason for that. We probably wouldn't get anything like this out of real life, but that's how it turned out for this set. And by the way, our coefficient of determination is 0.85, which means 85% of the reason why somebody might drink more or less caffeine than another person happens to have to do with how many finals they take. All right. So there we go. The nice thing is, once you have all that work that's done from doing the correlation coefficient, you've got a lot of pieces laying around that are going to be useful and necessary for doing the regression line, especially these means, these standard deviations, and this correlation coefficient. They're sitting around. They're just junk. They're leftovers. They're extra from what you've already done. We're going to reassemble them in a new way to get new information. Okay? So, as I've always said, when you get a data set that has 2 continuous variables, the first thing that you want to do is set it up in such a way that you can visualize it and have a good idea about what correct answers are going to look like at the end of the day, because you can intuit a lot. This might be the best line through those dots. It looks pretty good, right? But what if it was this line? This one's also pretty good. What if it was sloped a little bit differently? Nah, I don't like that one. It's a little bit low and I'm not sure how much. That one looks really good. It goes through this dot right here. Is that right? We don't know. So here's the thing. A lot of intuitively appealing lines go through these dots, and none are necessarily better than the other once we're close. So we got to figure out how to find out that line exactly. Since this line is good for predicting a y value from a known x value, we have to mathematically determine how to draw the line that minimizes our error in making those guesses. The method that we're going to use today will actually give you a line that is known as the least squares line. You will see least squares as a term in SPSS. When you start running things like this, it will say, what method to use? Least squares type 3. That's actually what it is that we're doing. But here's what it means to have a line that is the line that gives you least squares. If you took every dot in the scatter plot and drew a vertical line from that dot to the regression line, you would have the distance between the guess represented by the regression line and the actual data point for that person represented by the dot. That distance is error. The least squares line does this. It takes the distance of each one of those lines, squares the value, and then adds them all up to a sum. The line that we get from regression is the line that minimizes that sum. Any other line other than the linear regression line that we're going to draw today would result in a larger sum for the squared error values between that line and every data point. Okay, now the nice thing is, in order to get that regression line, we don't have to just draw all those lines, measure them with a ruler, square them, add them up, and then draw it again and see if we can do better, see if we do worse, and take a whole bunch of guesses. We're going to drive right for it with a procedure that doesn't look like we're doing any of that stuff. But I guarantee by the time we're done, we'll have a line that has this property. Okay? That was a little bit of intro. As I said, it's a short lecture. So before we move on, now that you've absorbed what it is that we're going to be doing, everything after this is mathematical procedure. But in the meantime, let me give you a little bit of classic deadpan one-liner comedian Stephen Wright. I call him the progenitor, the OG, the godfather of who came along later, Mitch Hedberg.
One time I went to the drive-in in a cab. The movie cost me $95. I've been arrested several times. I can't wait to be arrested and go all the way to the witness stand. If you swear to tell the whole truth and nothing but the truth, so help you God. Yes, you are ugly. Woman in the jury, I'd really like to sleep with her. Should I keep going, or are you going to ask me questions? If you shoot a mime, should you use a silencer? My grandmother was also insane. She had pierced hearing aids. Unscented perfume. Came in a little empty bottle. Then I tried to hang myself with bungee cord. I kept almost dying. And then I went into a store and I tried to buy something to put underneath the coasters. My uncle was a clown for Ringling Brothers Circus. And when he died, all his friends went to the funeral in one car. I'm going to court next week. I have been selected for jury duty. It's kind of an insane case. 6,000 ants dressed up as rice and robbed a Chinese restaurant. I don't think they did it. I know a few of them and they wouldn't do anything like that. My favorite chair is a wicker chair. It's my favorite chair because I stole it. I was at a party, a very crowded party where no one was looking. I went over to it and I unraveled it. I bought some powdered water, but I don't know what to add. I bought this thing for my car. You put it on your car. It sends out this little noise so when you drive through the woods, deer won't run in front of your car. I installed it backwards by accident. Driving down the street with a herd of deer chasing me. I remember when I was a fetus, I used to sneak out at night when my mother was sleeping. I thought to myself, you know, now's the time I should start stealing some stuff since I don't have any fingerprints. I was driving down the street 100 miles an hour for no reason. The police stopped me for speeding. They said, "Why are you going so fast?" I said, "Why? I had my foot to the floor." It sends more gas through the carburetor. Makes the engine go faster. The whole car just takes off like that. I said, "See this right here? See this? This steers it." Yeah, it's a small world, but I wouldn't want to paint it. So I'm laying there, and she says to me, "Let me ask you this." And I said, "What?" And she said, "If you could know how and when you were going to die, would you want to know?" And I said, "No." She said, "Forget it then." Every morning I get up and I make instant coffee, and I drink it so I'll have enough energy to make the regular coffee. I'm thinking about my grandfather and how he had a special rocking chair built that would lean forward rather than backwards so he could fake interest in any conversation. Woke up this morning, I was folding my bed back into a couch, and I almost broke both my arms because it's not one of those kind of beds. Bought a cordless extension cord. One time I went through a stop sign, they stopped me. They said, "Why do you go through the sign?" I said, "Hey, I don't believe everything I read." Doesn't matter what temperature a room is, it's always room temperature. I'm gonna get a tattoo over my whole body of me but taller. I've been getting into astronomy, so I installed a skylight. People who live above me are furious. I'm planning a trip to Spain, so I bought an album that teaches you the language. You put the album on, you put headphones on, you learn the language while you're sleeping. During the night, the record skipped. I get up the next day, I could only stutter in Spanish. I have an air conditioner in the window in my house. Last summer, I turned it around the other way. I turned it off full blast, and it got cold out. Watched the weather that night. They said it was supposed to be warm. I don't understand. And I was like this.
Hope you enjoyed that. All right. Then, last bit of last lecture. You might want to think back to when you were in high school and you were doing geometry, because you almost certainly dealt with linear geometry using an equation that you might recognize here. Y equals A plus BX. A couple of different versions of this, a couple of different labels for the variables, but you might recognize this as an equation for a line. That is to say, the y value is equal to some constant, which is the intercept, plus some other constant, which is the slope, times the x value. Y prime here, and that's how we pronounce it, y with the sky comma, the apostrophe, is y prime. Y prime is the y value that our regression would predict for a given x value. All of those predictions are going to lie along a line. So if you put in an x value, you apply this formula and you get a point, that point will be one of the points on our regression line. All right? X can be whatever it wants. You can pick any number of milligrams of caffeine from negative infinity to positive infinity. Y prime is determined by putting that X into the equation. So A and B are the ones that determine what the relationship is between any given X value and the Y prime associated with it. A is what's known as the Y intercept. It is where this line crosses the Y axis. And what happens at the y-axis? X equals 0 at the y-axis. Okay, so if you have a positive value for x, it's moving along to the right and it's left the y-axis. If you have a negative value for x, it's moving to the left, it's left the y-axis. But if x equals 0, you're right on the vertical line, you're right on the y-axis, and wherever our line crosses that, where x equals 0, is what A is, where our line meets the y-axis. B is the slope. And if you remember slope from back in geometry, that is the rise over the run. The amount of movement in the y dimension divided by the amount of movement in the x direction. That will tell you how many units to go up or go down when you move a unit to the right. All right? So the only question is, how do we go about getting these numbers? How do we get A and B? Once we have A and B, we have our line, because you can put in any value for x and get a y prime. And then any other value for x, get another y prime. And if you want to draw the whole line, you can just connect those dots and you'll have a line. All right. So here's a visualization of what we're going to be doing when we get our regression line. Here's the x-axis along this line. Here's the y-axis along this vertical line. A is going to be where the line crosses over the y-axis. Okay. Not where it crosses the horizontal line, it's where it crosses the vertical line. B is the amount of rise for a unit of run. The line itself is labeled as y prime, and it will be a good fit for all of the dots that are here in the scatter plot. All right. So again, the reason we don't have to worry about exactly what x and y prime are is because they're variables. They're free to vary. They will vary in lockstep with each other, but they don't have to be specified. They're variables. A and B do need to be specified. Here's where we start. We actually start with the hard part. We start with B. B seems like the more complicated constant to get, but we are ready to go and we need B to get A. Here's the equation for getting the slope. Here's the equation for getting B. B equals a reassembly of a bunch of stuff that you've already got left over because you did a correlation coefficient. And what it is that correlation coefficient, R, times the ratio of the standard deviation in y divided by the standard deviation in x. I'm not going to derive this for you, and you're not going to understand completely what's going on. But remember, if the slope is the rise over the run, this is a standard amount of change in the y dimension, in the up and down dimension. This is a standard amount of change in the x dimension. So right here, we've got a ratio of rise to run. This correlation coefficient tells you the tightness of that relationship. If it is a 1-to-1 relationship and it's perfect, that R is going to be equal to 1. And you're just going to have one standard deviation over one standard deviation, and that's your slope. But usually the relationship isn't quite so tight, and so that R becomes smaller, and therefore the slope gets a little bit flatter. Okay, that's all the explanation I'm going to put to it, but it makes sense. That will kind of help you to remember that the rise, the y dimension over the run, the x dimension, is what you're looking for. But please make this one of the formulas that you are kind of obsessive about checking when you do your final and you go to the formula sheet, to make sure that you've put the right standard deviation on the top and the correct standard deviation on the bottom. In our example, the slope then is going to be the correlation coefficient, which was 0.92 times 0.57. That was the standard deviation in the number of finals, divided by 225.2. That's the standard deviation in the number of milligrams of caffeine. In this case, we end up getting 0.002, a alarmingly small number. Why is that? That's because this is the number of finals in the y dimension, the rise, for every 1 unit in the x dimension, the run. 1 unit in this case, though, is 1 milligram of caffeine. And people are drinking over 1,000 milligrams of caffeine a day. So that's a very small increment for caffeine, 1 unit, which means we should also have a very small increment in the number of finals. That happens to be 2 1,000ths of a number, all right? So what this slope means is that for every single milligram of additional caffeine, a person is likely to have 2 1,000ths more finals per semester. Now you start racking up 100, 200, 300 milligrams of caffeine at a time that differs one person from another, and you get a reasonable number of increase in finals. That's how it's going to work. All right. Now that we have the slope, we really only have one missing element in that equation to get the regression line. That's A. That's the intercept. But it might seem like we're stuck. What we need to know then is something about that line that will anchor it to a point in space. We know its slope. We know that it is oriented in space this way, but it could move anywhere up and down, side to side, I suppose, and be an infinite number of lines. Okay, but if we can take a slope and nail it to even one point in space, we can then extrapolate every other line that line crosses. Here's the nice thing. Every regression line always goes through the point that is defined by the x bar, the average value of x, and y bar, the average value of y. We know what x bar, y bar is because we did a correlation. We had to have that in order to get the z-scores. So this point right here, that is at the average value of milligrams of caffeine, combined with this point here, which is the average number of finals, is x bar, y bar. The regression line will always go through that point. If you have an average score on x, our best prediction is always going to be that you have an average score on y. Now, can I point out a common mistake without tempting you to make that mistake? A lot of times people get confused when they start drawing their regression lines on the homework or on the final. They say, oh, it goes through that point where the lines cross. And they put their regression through the origin. No. Okay, there's no reason why regression has to go through the origin. There's no reason to think that a 0 in caffeine would mean you took 0 classes. The regression line may or may not go through the origin, but it probably doesn't. But the regression line always goes through the point x bar, y bar. So since we now know this point and we know what the slope is, we can now walk back 1,150 units, subtracting 2/1000ths of a final each time to figure out what the guess on finals is going to be when the number of caffeine milligrams equals 0. All right, so now that we know a point and we know a slope, we can get the intercept, whatever it might be. And again, we haven't quite figured that out yet. All we have is a little bit of a guess. All right, the equation for the line, taking a step back here, is y prime equals a plus bx. Since we know that if we swap out x for x bar and we swap out y prime for y, we will get a set of values that makes this equation true because x bar, y bar falls on the line. So y bar equals whatever a is plus b times x bar. Since we're after a, everything else is known, we're after a, we can rearrange this equation and say a, the y-intercept, the place where the line crosses the y-axis, is equal to the average y value minus the slope times the average x value. So this is exactly what I'm saying, all right? What do you mean, Enos? What is that exactly what you're saying? When I was right here, I said, look, that's y bar right there. We're going to step back 1,150 units, subtracting 0.002 each time. That's exactly what this tells us to do right here. Take the average y value, subtract 0.002, the slope, multiply it by x bar, which is 1,150 units. So if we just fill in the values that we had from our correlation coefficient, this known stuff that we've already worked with, we get 3.14, the average y value, the average number of finals, minus 2 finals for every milligram of caffeine times the milligrams of caffeine in an average person. That means A equals 0.84. So the entire regression equation is now known. Our best guess at a person's number of finals is equal to a baseline of 0.84 finals plus 2/1000ths of a final for every extra milligram of caffeine. Okay, now we can predict a number of finals from any given number of milligrams of caffeine. So let's say somebody walked in off the street, they were new, they were not in our data set before, and we said, hey, how many milligrams of caffeine are you drinking per day? And they said, I am drinking 1,312 milligrams of caffeine. Boom, we put it into our regression equation, we get this. 0.84 finals plus 0.002 times your X value, 1312. That's a 2.62 for the caffeine, 0.84 for baseline. Add them together. I predict that you are taking an average of 3.464 finals. Now, that may be right. That may be not right. That may be close to right. That may be far from right. But it is our best guess for this new person's performance information based on all the people who have come before. So that leads us to our last question. Once we have that line, how good a line was it through the dots that have come before? Okay, that number is called the standard error of estimate. We are using this line to do an estimate. We want to know the standard amount of error that will come from our estimate. What this is, and this whole process should look pretty familiar, but what this is a standard deviation for the length of the distance between each data point and the line that we've predicted. So there's essentially an entire data set lurking in what we've done, which is a data set made up of the values of the length of these lines. This line from this point to the line has a value. This dot to the line has a value, this dot to the line. So here are like 4 values in terms of the green lines that would make up a new data set. If we get the standard deviation for that data set, we've got our standard error of estimate. Make sure that what you're doing, since we are making guesses in the vertical direction for the Y variable, that you're always talking about the distance between a data point and the line in the vertical dimension. You're not looking for this. Okay, this is the shortest distance between that line and the data point, but it's not what we're after, because that would actually make a prediction across 2 different X's, the X where you started your dot and the X where you ended up on the line. No, that's not what we're after. This is just stupid. Don't even think about drawing vertical lines, okay? No. So what we're after is the standard deviation of the length of all the lines that separate the dots in the scatter plot from the line of our regression. That means in order to get that distance, you would subtract for every person the Y value that they actually had from the Y prime value that their X value predicted. Take the difference between those two, square it, add them all up to get a sum of squares, put it over the degrees of freedom, which in this case is n minus 2. 10 people, in this case, minus 2 is going to be 8. Take the square root, you've got your standard error of estimate. Now, it's not a terribly complex equation, it's not a terribly complex procedure, but you have to do a lot of work for each person, so it is, as we've gotten to understand, a pretty repetitive thing. That's why I've only given you 2 examples out of 10 and just assume that you could do it 8 more times in the row that says etc. All right, so here's what would happen for person number 1. They had 1,378 milligrams of caffeine. They actually took an average of 3.55 finals. But if you took 1,378 and put it into this equation, took 0.84 plus 2/1000ths for every milligram of caffeine and 1,378 of those milligrams, you would get 0.84 plus 0.002 times 1,378. That is 3.6. It's not 3.55, that's reality. 3.6 is the guess that we got from our regression equation. Those are pretty close, not going to contribute a lot of error, but when we get the difference between the two, we get a 0.05 difference. When we square it, we get 0.0025. That is the contribution of person 1 to the sum of squares that is at the top of the numerator of this equation underneath the square root. For person number 2, 956 milligrams of caffeine. If you put that into the regression equation, it would have predicted 2.75 finals. In reality, that person took 2.65 finals. The difference is 0.1. If you square that, you get 0.01. Again, if you added up that for every single person, all 10 of them, the grand total would have been 0.42. Not a lot of error. As I said, this happens because we have a very big, strong correlation coefficient. All of the data points are clinging really closely to this regression line. It's doing a really good job of minimizing the error on our guess. Anyway, so the error term here is 0.42. That now becomes the numerator in this equation. There were 10 people in the study. There's n equals 10. 10 minus 2 is 8. So 0.42 divided by 8 is 0.0525. Take the square root, and your standard error of estimate is 0.229. What that means is that if somebody gives me their milligrams of caffeine and I want to guess how many finals they've taken, I can honestly share that I'm typically off by between 20% of a final and 25% of a final. All right, so I'm going to get it pretty close, but there's a little bit of room for error there. How did that happen? Stats got over. Grasshoppers, that is all I have to share with you. Once we go beyond that, I kind of get a little bit murky myself. The person who needs to pick up your education from here on out, if you want to do more with multivariate statistics, if you want to do more beyond what we've done here, you need to sign up for Dr. Marshall's 400 level advanced statistics class and be the hot shot in your graduate program for people who already get the complex stuff. In the meantime, though, you should at this point have the tools, both conceptually and the basic toolbox with SPSS, to do the things that your professors might ask you to do in 301, and hopefully most of the things that I might ask you to do to deal with data sets that would come from any research you're doing in their labs. Okay? I hope that this goes very well for you when it comes to the final. I hope that it's been good enough to watch videos without being able to ask questions to get this material into your heads. I hope that you will join me on the video chat to ask questions if you have them. And in the meantime, if you need extra credit, go for the extra credit problem that's posted up online. Make sure that you turn in your SPSS assignments. Make sure that you turn in this last in-class assignment. Put that all together to be armor as you go into the final and do your very, very best there, okay? Take care, everybody. I hope I get to see all of you as soon as possible in the fall. But again, we never know. Take it easy.